Okay, so up to now, we've looked at forces that were moving horizontally or vertically, and we looked at how we needed components of forces that were also moving horizontally or vertically. Another way to think about that is that we needed parallel and perpendicular components of those forces. Vertical is parallel to horizontal. So we got the horizontal and the vertical components. Well, now we're going to look at objects that are moving on an inclined plane. And once again, we're going to want components that are parallel to the inclined plane and perpendicular to the inclined plane. We want components that are parallel and perpendicular to the direction of motion of the object. In this example, we've been told that a particle P with an unknown mass m is on a slope of 30 degrees and there's a force of magnitude 5g acting at an angle of 60 degrees to the slope. All of this is causing the particle to accelerate up the slope at 0.5 meters per second squared. So we have a show that question where we're trying to find the mass. So let's go ahead and model all of this in a well-crafted diagram. So I already made a start on this. I've got the 30 degrees. I've got the unknown weight of mg. I've also drawn its components, its parallel and perpendicular component, and I've got the reaction force as well. Here is the force being applied to the object at 60 degrees to the slope. And I also need to be really careful to get a perpendicular and parallel component here. So perpendicular approaches the slope at right angles, and then the parallel is as it is. Okay, so the question has told us that this particle is being pushed up the slope. So the positive direction I'll take as up, and we know the acceleration 0.5 meters per second squared. Here we have 30 degrees. We can prove that to ourselves since we have 90 degrees here and we know the final angle in the original right angle triangle, which means we can get these components, mg cosine 30 and mg sine 30. Components for the force over here, 5g sine 60 and 5g cosine 60. So we've just about labeled everything that we need, and we can actually start to solve by resolving in appropriate directions. The appropriate directions are parallel to the slope and perpendicular to the slope. We'll start with the perpendicular so we can find the reaction force. Well, the reaction force should equal the two parallel forces that are going down, mg cosine 30 plus 5g sine 60. We'll go ahead and resolve parallel to the slope now. And we're using F equals ma. Positive direction, we have 5g cosine 60, and the negative direction is the mg sine 30. So that resultant force should equal the mass times the acceleration. Okay, so using this, let's try and make m the subject. So just some smart rearranging, get all of the m terms onto the right-hand side. We'll go ahead and factorize, and then we'll divide by this bracket. Well, from here, we know the values of cosine 60 and sine 30. They're both going to be a half. So let's just factor that in. And this is really close to what we were asked to show. I'm just going to double the top and double the bottom. And here we have an expression we were asked to find. And we can show that the mass is 5g over 1 plus g kilograms. Okay, let's have a look at a slight variation on a standard question. So we still have the slope, which is at an unknown angle. And we have our particle. I like to draw these as boxes, which has a mass of 2 kilograms, so weight 2g. Let's get those parallel and perpendicular components on. We're also told that there's a force that is pushing this particle up the slope with a force of 4 newtons. And here's our unknown angle. We'll get back to that. Let's just finish the diagram. Okay, reaction force as always. And I think we can assume that the positive direction is up the slope. So we'll choose this as our positive direction. Okay, alpha. We were given the information that tan alpha equals 3/4. Now this is a technique you've probably come across in pure maths, where we can set a diagram that matches this situation, use Pythagoras to find the hypotenuse, and then we can generate expressions for sine alpha and cosine alpha, being 3/5 and 4/5 respectively. And we'll use these in our calculations going forwards. So let's just finish off the diagram. Here we have 2g cosine alpha and 2g sine alpha. I don't want you to ever try and calculate alpha. We're going to use these expressions throughout all of our working out. It will maintain accuracy, and it's a little bit easier than working with an unwieldy decimal value. So we'll go at this with our usual strategy. We'll start by resolving perpendicular, so we can get an expression for r. R should equal 2g cosine alpha. Cosine alpha is the 4/5. Altogether 8/5g. All right, now let's resolve perpendicular. So here we're going to be using Newton's second law, F equals ma. The forces in that parallel direction are the 4 newtons and the 2g sine alpha. Resultant of those equals mass times acceleration. Do some substituting once again. And we're trying to find the acceleration, so let's make a the subject. And that gives us negative 3.88 meters per second squared. Now, the fact we have a negative is very important. We chose up the slope as the positive direction, so a negative value really lets us know this particle, this box, this object is moving down the slope. It's moving in the negative direction. Just be careful about that in any sort of interpretation question or in any question in general. We need to be able to understand our model and what the negatives or positive values actually mean in context.